Hi, this is Charlie, and today we're going to go over Lab 4 on temperature. So we're going to talk about temperature scales, the three common temperature scales, how to convert back and forth between Celsius and Fahrenheit, and then we're going to talk about the effect of heat and wind on the human body. We'll talk about wind chill and look at the heat index. And then we'll talk about temperature controls. Temperature controls are the factors that create patterns of average temperatures. So over the course of a year, where is it hot? Where is it cold? And then we'll look at annual temperature range. Temperature range is the difference between summer and winter temperatures. And we'll look at the patterns, the slightly different patterns that result from temperature range. Yeah, I hate all that. I'm going to start over. Hey, welcome back. This is Lab 4 Temperature. I'm Charlie Thompson, and today we're going to go through Lab 4. So we'll talk about temperature scales, the difference between Celsius and Fahrenheit and Kelvin. We'll talk about the effect of temperature on the human body. We'll look at the wind chill and the heat index. And then we'll look at temperature controls. And temperature controls are the reasons for the patterns of average temperatures, like the tropics are hot and the poles are cold, and annual temperature range. Temperature range is the difference between the summer temperatures and the winter temperatures. Some places have a big range, some places have a small range, and we'll talk about all of that. So first off, temperature scales. We've got Kelvin, Fahrenheit, and Celsius. I'd like to point out everybody in the world except for Liberia and Myanmar uses Celsius. The United States, Liberia, and Myanmar are the only countries that use Fahrenheit. Scientists use Kelvin. Why do they use Kelvin? Well, they use Kelvin because temperature is just a measurement of kinetic energy. The higher the kinetic energy, the higher the temperature. The lower the energy, the lower the temperature. So absolute zero represents the temperature at which point there is no energy. If there's no energy, the temperature is absolute zero, which is on the Kelvin scale, named after Lord Kelvin. We're not going to use Kelvin. 0 degrees Celsius works out to 273 Kelvin. There are no plurals. I don't know why. Like we'd say, whatever, Celsius degrees, but it's not kelvins. It's just 273 Kelvin is the melting point of ice. Sorry, let's put that down here. 273 Kelvin is the melting point of ice. 373 Kelvin is the boiling point of water. So 1 Kelvin degree is the same as 1 Celsius degree. You can see with Celsius, between melting and boiling, it's 100 degrees. And same thing on the Kelvin scale, from 273 to 373 is 100 Kelvin. The Fahrenheit scale. The Fahrenheit scale, developed by Daniel Gabriel Fahrenheit, and he set 0 as the temperature that he could get a mixture of crushed ice, water, and salt. So he was trying to duplicate a frozen ocean. And when he got this optimal mixture of ice and salt and water, he just said, well, that's 0. So on the Fahrenheit scale, water boils at 212 degrees Fahrenheit. Ice melts at 32 degrees Fahrenheit. And let's talk about Celsius. It's a way better system. Everybody else uses it. Water boils at, again, this is a temperature, so we're going to say at 100 degrees Celsius. Ice melts at 0 degrees Celsius. There's a bunch of different temperatures that water freezes at, but for whatever reason, it always melts at 0. So enjoy that. Temperatures. A temperature is just what it is, or what it was. For example, 65 degrees Fahrenheit or 19 degrees Celsius. Those are temperatures. Degrees are the number of degrees between two temperatures. Now, there's nothing else that you have to deal with this except temperatures, so I'm just going to continue and things are going to get a little bit weird for a minute. Right. So the difference between degrees Celsius and Celsius degrees gets confusing. Nothing else works like this. It's not that you would have $20, but you need to go to the bank to get $20 more. Well, temperatures work that way. So the amount that you have would be like the temperature. What is it? It's 65 degrees. I've got $20. But if it gets warmer by 5 Fahrenheit degrees, and that's the way you have to say that, it would be 70 degrees. But you never have to say, I have to go get $20 more if you're talking about a number of dollars. Degrees works that way. So degrees Celsius is a temperature. Temperatures are written the same way we give a temperature. I would recommend trying to remember it that way. I mean, the way you say, you never talk about degrees, you always talk about temperature. So what temperature is it? 65 degrees. 65 degrees. We don't say Fahrenheit because we just assume if we're in the US, everybody's dealing with Fahrenheit, but we should say it's 65 degrees Fahrenheit, and that's the way you give a temperature. So you'd say water boils at 100 degrees Celsius. You would say ice melts at 0 degrees Celsius. Those are temperatures. Celsius degrees and Fahrenheit degrees are the number of degrees between two temperatures. So they're written differently. Celsius degrees. Water boils at 100 Celsius. That's a temperature. Ice melts at 0 degrees Celsius. That's a temperature. But there are 100 Celsius degrees between 0 degrees Celsius, that's a temperature, and 100 degrees Celsius, that's a temperature. Here, 100 Celsius degrees, that is a number of degrees between two temperatures. So with Fahrenheit, water boils at 212 degrees, ice melts at 32 degrees. So between 212 and 32, there are 180 Fahrenheit degrees. There are 180 Fahrenheit degrees between 212 Fahrenheit and 32 degrees Fahrenheit. On the Celsius system, water boils at 100 degrees Celsius. Ice melts at 0 degrees Celsius. But there are 100 Celsius degrees between freezing and boiling. There are 100 Celsius degrees between 0 degrees Celsius and 100 degrees Celsius. The easiest way to remember this is just remember you already say temperatures correctly. 0 degrees, that's a temperature. If the last thing is degrees, it's a number of degrees. 100 Celsius degrees. So the last thing is degrees, so those are a number of degrees. And now you can test yourself. 60 degrees Celsius, temperature or degrees? It's a temperature. 60 Celsius degrees, the last thing is degrees, so that's got to be a number of degrees. 32 Fahrenheit degrees is a number of degrees. 32 degrees Fahrenheit, that's a temperature. So one of the reasons you really need to pay attention to this is the way you convert degrees is different than the way you convert temperatures. With degrees, you know that there's 180 Fahrenheit degrees between boiling and freezing, and there's 100 Celsius degrees between boiling and freezing. So if we divide both sides by 10, we get 18 Fahrenheit degrees equals 10 Celsius degrees. If we simplify that down to 1 Celsius degree, 1.8 Fahrenheit degrees equal 1 Celsius degree. So every time the temperature goes up by 1 Celsius degree, the temperature would go up by 1.8 Fahrenheit degrees. So to convert back and forth, you just are either multiplying Celsius by 1.8 to get Fahrenheit degrees, or if you have Fahrenheit degrees, you divide by 1.8 to get Celsius degrees. That's it. You're done. Either divide or multiply by 1.8, depending on which way you're going. If you remember that ice melts at 0 degrees Celsius, and that water boils at 100 degrees Celsius, that's 100 Celsius degrees, so 100 Celsius degrees equal 180 Fahrenheit degrees. Temperatures, though, different. 212 degrees Fahrenheit equals 100 degrees Celsius. 32 degrees Fahrenheit equals 0 degrees Celsius. Those are temperatures. So we already know that 1.8 Fahrenheit degrees equal 1 Celsius degree, but there's this 32 degree fudge factor. So the formula to convert from degrees Celsius is degrees Celsius times 1.8 plus 32 equals degrees Fahrenheit. To go from Fahrenheit to Celsius, Fahrenheit minus 32 divided by 1.8 equals degrees Celsius. So it's still divide and multiply by 1.8. But when you're going from Celsius to Fahrenheit, you got to add 32. When you're going from Fahrenheit to Celsius, the first thing you got to do is subtract 32 degrees and then divide by 1.8. So here's the two conversion factors, going from Celsius to Fahrenheit, going from Fahrenheit to Celsius. So I have a small brain and I like to use numbers that I know I'm going to get it right so that I can test myself. So we already know what 100 degrees Celsius is in Fahrenheit, but let's see if this works. So we've got 100 degrees Celsius, multiply that by 1.8, that gets us to 100 plus 32. I'm sorry, 100 times 1.8, that's 180. 180 plus 32 is 212 degrees Fahrenheit. Boiling point of water Celsius, boiling point of water Fahrenheit. Check, check. Let's do another one. 32 degrees Fahrenheit. We already know what the answer is in Celsius, but it's a good way to make sure that you're using the formulas correctly. So in this case, it's going to be Fahrenheit minus 32, divide by 1.8, 0, it's 0. That is, 32 minus 0. 32 degrees Fahrenheit equals 0 degrees Celsius. So let's look at another one, 10 degrees Celsius. So it's going to be 10 times 1.8 is 18. 18 plus 32 is 50, so 10 degrees Celsius, 50 degrees Fahrenheit. 50 degrees Fahrenheit, 50 minus 32, 18 divided by 1.8, 10 degrees Celsius. So 50 degrees Fahrenheit equals 10 degrees Celsius because they're both temperatures. All right, wind chill. That's pretty simple. Cold plus wind equals colder. This is the wind chill chart. And here's the way we're going to use it. We're going to find a wind, or a temperature rather, Celsius in parentheses Fahrenheit. You know that because over here when you're reading the diagram, which is part of the student learning outcomes for this class, be able to read a scientific diagram, actual air temperature in degrees, degrees Celsius, so you know their temperatures, and then in parentheses degrees Fahrenheit. So all the numbers in parentheses are Fahrenheit, and down here it's got wind speed in kilometers an hour, and then miles per hour in parentheses. So all these parentheses are these are miles per hour, kilometers per hour, miles per hour, and then these are all temperatures again, degrees Celsius, degrees Fahrenheit. So if it was 4 degrees Celsius outside and it was calm, the temperature would be 4 degrees. If it was 4 degrees Celsius with a 16 kilometer an hour wind, the temperature would be 1 degree Celsius. If it was 4 degrees with a 64 kilometer an hour wind, the temperature would be -3 Celsius. All right, heat index. It's a dry heat. You hear that a lot about Sacramento. Yeah, it's hot in the summer, but it's a dry heat. Well, why is that? Well, that's the heat index. The heat index compares temperature and relative humidity. Our bodies cool themselves by the evaporation of sweat. It's not the sweating. The sweat has to evaporate. Oh, right. Because every gram of water that evaporates is going to take with it 540 calories of heat from your body. Every gram of water that evaporates off your skin takes 540 calories with it. So as the relative humidity is higher, there's less energy available to evaporate water, so you just feel hot. In fact, if the relative humidity is high enough, you're just going to sweat all day long. None of it's going to evaporate. You're just going to be sweaty and miserable. And let's see how to use this. All these numbers are degrees Fahrenheit because this is the National Weather Service heat index table. So just like we did with the other numbers, we're going to find a temperature, 110, and a humidity, 5%. So across the top, temperatures in Fahrenheit, across the side, relative humidity. So if it was 110 with 5% relative humidity, it would feel like a balmy 101 degrees Fahrenheit. It would actually feel cooler than it is because it's so dry that so much sweat is evaporating that you're cooler. What if it was 110 degrees with 5% relative humidity? We just did that. What if it was 104 degrees with 5%? The temperature would be 96 degrees. Same temperature, 104, but at 50% relative humidity, it's going to feel like 131 degrees, which would be miserable. In fact, that would be in the extreme danger category. So you find the temperature, you find the humidity where they cross, that gives you the heat index temperature in degrees Fahrenheit. Let's talk about the principal temperature controls. I think I could summarize this by saying it's cool to be high. High temperatures in the mountains, it's cold. High latitudes are the poles, it's cold. So the main control on temperature is going to be latitude, followed by land-water heating differences. I'll talk more about what that means. Ocean currents and sea surface temperatures have an effect on temperature. And elevation is going to play a role in temperature patterns. So latitude is going to control average temperature. The tropics are hot, the poles are cold. That should be obvious. That's pretty much the way it works. High latitudes are cool. High latitudes are at the poles. Low latitudes are hot. Low latitudes would be like the equator. They have the lowest latitude number, 0. So low latitudes are by the equator. High latitudes are at the poles. Latitude is also going to control the temperature range. High latitudes have a high temperature range. Low latitudes have a low range. So there's this inverse relationship between average temperature and temperature range, that high latitudes are cool, but they have a high temperature range from summer to winter. Low latitudes, like the tropics, are hot year-round, and they have a low temperature range. So let's look at this. Forest stations were 13 degrees south in Brazil. So it's a low latitude, so the temperature should be high. Check, about 80 degrees. And the temperature range should be low. You can see going from summertime to wintertime, not a whole lot of difference, just a couple degrees. As we move from 13 degrees away from the equator to 30 degrees away from the equator. So now you can see the temperature curve. It's peakier. There's more of a difference from the summer high temperatures to the winter low temperatures. So the temperature range is higher, and the average temperature, instead of 80, looks like it's in the low 70s or the high 60s. As we move farther away, we could go to Montreal, Quebec, 45 degrees north. So the average is lower. Looks like it's in the 40s now, and the range is higher. So looks like here the range is, I don't know, maybe 3 degrees. And from here, it looks like the range is from, well, let's see, that's -7, that's -12. So let's just call that -10 to, I don't know, 22. So like 32 degrees Celsius, 32 Celsius degrees. Let me say that correctly. 32 Celsius degrees between -10 Celsius, that's a temperature, and 22 degrees Celsius, that's a temperature. So higher latitudes have lower temperatures, but a higher range. High latitude, high range. Low latitude, low range. Land-water heating differences refers to the differences between the way water heats up and the way the land heats up and cools off. Water heats and cools much more slowly. In fact, it takes more energy to change the temperature of water than everything else on the planet. In fact, it takes 4 times as much heat to change the temperature of water as it does to change the temperature of the land. 4 times as much heat. Places by the coast have small temperature ranges. Places inland have high temperature ranges. And we call this continentality. The farther inland you are, inland locations are continental locations. Continentality refers to the property of being inland. Marine climates or maritime climates are on the coast. Coastal climates we call marine or maritime climates. Inland climates are continental climates. So some of the differences I mentioned, it takes 4 times as much energy to change the temperature of water. It takes 4 times as much energy to change the temperature of water as it does to change the temperature of land. You know this if you've ever been to the beach. First thing in the morning, the water is cold, the sand is cold. In the afternoon, the water's still cold, but the sand is broiling hot. So here's the reasons for that, and the biggest is it takes 4 times as much energy to change the temperature of water. Other reasons, less evaporation. When water gets warm, it evaporates, and that pulls the heat out of the water because the heat energy is what made the water evaporate. So that actually, when water evaporates, it takes the heat energy with it and goes away, goes someplace else. Ocean's water is transparent, so it heats up, the sun shines and heats up a larger volume. So water's already harder to change the temperature of, and now instead of the sun shining on just the top layer of dirt, it's heating up hundreds of feet of water. Also, when that water gets warm, some of it's going to evaporate, cooling the water that's left behind. And the water mixes and moves. So the warm water that was at the top, maybe it gets mixed up, and now it's brought cold water to the surface and warm water underneath. So water moves around, it mixes, the land doesn't. The land just gets hot or the land just gets cold. So the ocean, big lakes don't change temperature a whole lot during the course of a year. The land changes temperature dramatically. And all of that we summarize and put under the label of either continentality or land-water heating differences. Continentality is the idea if you're farther inland, there's bigger temperature ranges, but the reason for continentality is land-water heating differences. So here we've got two different cities. San Francisco, I think you've heard of that. It's on the coast. Wichita, Kansas, it's in the middle of the country. So here's the temperature curve for San Francisco, going from 50 degrees Fahrenheit to like 63 degrees Fahrenheit. So like a 14.6 degree annual temperature with like a 13 Fahrenheit range, as opposed to Wichita, Kansas, going from 32 to 80. So almost, was that 48 degree range, 48 Fahrenheit. The average temperature is about the same, 14.6, 13.7, but you can see San Francisco has a very small range, and Wichita, Kansas, in fact, well below freezing in January, and in the 80s in the summer. San Francisco looks like it's hitting a high average temperature of, 63, 64 degrees, because it's right on the coast and surrounded by so much water. So land-water heating differences, this would be the difference between a continental climate like Wichita and then a coastal or maritime or marine climate like San Francisco. So ocean currents and sea surface temperatures will play an effect. Warm currents occur off of all of the east coasts. Cold currents off all of the west coasts. Did I say coastuses? Warm currents evaporate more easily. So the Gulf Stream and the Gulf of Mexico, for example, is going to evaporate. Lots of water evaporates, goes into the air, so they get lots of rain in the winter. They get lots of rain in the summer. We don't get any rain in the summer for the most part because we have a cold current. The Gulf Stream is a warm current, so they get extra moisture for summer rain. Here is average sea surface temperature, or sea surface temperature on the 23rd of July in 2014. You can see the cold in the northern hemisphere. The oceans rotate clockwise. So there's a warm current going up the east coast and a cold current going down the west coast. A warm current going up the east coast, cold current coming down the west, cold current coming down the west, cold current coming down the west, warm current going down the east, warm current going down the east. You can see how much farther down the warm current is coming and how far up the cold current is coming. Same thing over here, warm current coming up, cold current coming down. So really that's going to have a role in summer rainfall. If there's a warm current offshore, your average temperatures would be higher. In fact, this warm current goes over to Europe and dumps heat to Europe and keeps Europe warmer in the winter. The reason a lot of European ports don't freeze is this warm water that circulates, goes across the equator, goes up the east coast, then goes over to Europe and dumps heat there. Elevation. High elevations are cool. If you think about where people go skiing, is it high elevation or low elevation? High elevations. So let's look at the pattern of average temperature, and already I can see, because I'm looking at it, I can see a couple patterns. So first, the tropics are hot, the poles are cold, over 25 Celsius, below 21 Celsius. So the overall pattern, latitude, and I'd say it's latitude modified by elevation. For example, you can see this colder yellow. The yellow is colder, goes blue, and then green, then yellow, then orange, then red. So you can see this little strip of yellow. Those are the Andes, where there's higher elevation. You can see these little pockets of blue. Those are the Rocky Mountains. You can see this little yellow sticking down. Those are the Appalachians. If you could zoom in a bunch, you would see California, the Sierra Nevadas. They are high and cold. This is the Ethiopian highlands. You can see the little yellow area in the dark red. It's higher and colder. In Papua New Guinea, you can see there's a little strip of yellow in the middle of the island. That's because it's very, very high. In fact, it's so high on the equator in the Andes, right here, that there are glaciers on the equator. They're at 26,000 feet above sea level in the Andes, but you can see the obvious effect of elevation on temperature. High elevation, low temperature. Right here, India, super hot. Saudi Arabia, super hot. At the same latitude as Saudi Arabia, where it's super hot, is the Tibetan Plateau, where it's super cold. The average elevation about 15,000 feet above sea level. That's about 3 times as high as Denver. So you can see the overall pattern is latitude as modified by elevation. It's cool to be high, so high elevations are cold, high latitudes are cold. Next up is the temperature range. This is the difference between summer and winter. And I'll post the slides, so if you want, you can go back and forth and compare average with range, average with range, average with range. So the temperature range now, there's a slightly different pattern. It's still latitude, right? At the equator, the lowest ranges found across the equator. As you move away from the equator, it gets higher. So latitude is going to be key, but now I'm not seeing the same necessary effect of elevation. Like the Tibetan Plateau kind of has disappeared. So elevation not as important with temperature range. Continentality is going to be the big driver. So it's going to be latitude and continentality are going to drive temperature range. So you can see these concentric circles as you move away from the coast, the temperature range gets higher and higher and higher. Same thing in Eurasia, although on a slightly different manner, because as you move from west to east and move inland, the temperature range goes higher and higher and higher and higher and higher until the highest range is found right here in Siberia. It's a 183 Fahrenheit degree range between the winter low of -100 and the summer high of about 83 degrees Fahrenheit. And the reason that it's shifted over to the east is in the mid-latitudes where we live, the prevailing winds are from the west. They blow from the west to the east. So there's ocean right here, but because the prevailing winds are coming out of the west, it doesn't matter that there's ocean right here. By the time air is here, it's had to travel all the way across Eurasia. So the pattern, again, the highest temperature range, high latitude, well inland, and then shifted a bit to the east because the prevailing winds are coming from the west. Also, you can see the importance of continentality because in the northern hemisphere, it looks like the highest is about 72 Celsius degrees. In the southern hemisphere, I'm not seeing anything, a temperature range higher than like 30 degrees. So if you compare, for example, Canada with South America, and part of that, again, so here's the equator, here is the Tropic of Capricorn. So that's 23. So this is going to be like 30 degrees. Let's see, what do we have? 10. Oh, these are 20-degree chunks. That's 20, that's 40. So at 40 degrees south, you got this little sliver. 40 degrees south, there's nothing. 40 degrees south, you're in between Tasmania and the rest of Australia. 40 degrees south, there's just a little bit of New Zealand. At 40 degrees north, you've got the entire width of the United States. At 40 degrees north, you've got the entire width of Eurasia. So way more landmass in the northern hemisphere. So there's way more continentality because there's way more continents. The combination that gets you a high temperature range is high latitude and well inland. In the southern hemisphere, there's just nothing at high latitude. There's no continents at high latitude. So the temperature ranges in the southern hemisphere are much, much, much smaller than they are in the northern hemisphere. Temperature range, again, a function of latitude and continentality. So here, another average temperature. It's going to be latitude and elevation. You can see again the Tibetan Plateau, the Ethiopian highlands. If this was zoomed in more, you could see the European Alps. You can see the Rockies up into Canada. You can see the Appalachians. You can see the Andes, those yellow streaks across South America, right from the Amazon. So same latitude as the Amazon rainforest, there are glaciers, except they're at 26,000 feet. Average temperatures across the U.S., so it's mainly latitude. Like here across the Plain States, there's almost no difference in latitude. No difference in elevation as you go up in latitude. So the pattern of temperature, pretty much latitude. Here you can see the Appalachians, higher elevation. causing colder temperatures. The Rockies, higher elevations, colder temperatures. The Sierra, higher elevation, lower temperatures. The Mexican Cordillera, the mountains in the inland of Mexico, higher elevation, lower temperatures. And then temperature range. Again, global patterns of temperature range. It's going to be latitude and continentality. Again, Siberia has the highest temperature range. And here we have the pattern of temperature ranges across the United States. So across the plain states, again, you can see it's just pretty much latitude. There's a smaller effect of the Appalachians, a much smaller effect of the Sierras, a smaller effect of the Rockies. Really the big standout for me with temperature ranges, the land-water heating differences with the Great Lakes. They're made of water, so they heat up and cool off, so they have a way smaller range than everything around them. So if you compare the temperature range numbers for over 46 degrees right here with, 20 or 30 degrees in the middle of the Great Lakes. So land-water heating differences with annual temperature range, it's primarily going to be latitude and then continentality. Again, those concentric rings as you move inland and inland and inland at the same latitude. So that's one way you could check that. At the same latitude, the temperatures go up and up and up and up and up as you go inland. The temperatures go up and up and up and down because of land-water heating differences, and then right back up. And then here is elevation across the United States. I thought I should go over this so that everybody knew what I was talking about when I'm talking about the Appalachians. These are the Appalachian, also called Appalachians, Appalachian Mountains across the East Coast. Here is the lighter brown, I guess is a better, the lighter brown regions, the Canadian Rockies, the American Rockies, across Colorado up to the Colorado Rockies, from Colorado up to Idaho, and then the Canadian Rockies. Here are the Sierra Nevadas. Here's the Cascades. So there's mountains. And then you can also see some of the mountains in Mexico. But for North America, for the United States anyway, the Appalachians are important. The Rockies, this higher area in here, and then the Sierras are going to be the main areas, along with the Mexican Cordillera, the higher elevations in Mexico. And that's it for this lab. I wish you good luck on Lab 4 and temperatures.